All right, we are looking at lesson 4.5. Lesson 4.5 says Summary of Curve Sketching. This is the title of this entire section, Summary of Curve Sketching. So basically, if we could take everything that we've learned this semester and we could tie it in one big package and put a bow on it, it would be this lesson. Okay? Your final in this class will consist of problems from this section. Okay? So if you want to know, like, what does this look like? This is the whole enchilada, and it's one section in one place. I took pictures just now of the textbook from pages 351 and 352 and 353, where they have guidelines for sketching a curve. So if I were you, I would mark in your notes places where you can reference. How do I find the domain of a function? What does it mean by find the range of the function? How do I check for symmetry? What does it look like to have a horizontal asymptote, vertical asymptote? Okay, and we'll walk through those things pretty quickly here. For some reason, my textbook is not populating pictures very well. Like down here, it says the graph of an even function, and I'm supposed to be able to see figure 4.57, but I can't because I love that. So we're just going to have to pretend that we can see things. But it still tells you the words. Guidelines for sketching a curve. You have to know the properties of the function. You have to know whether it's a logarithmic function, and I don't take logs of negative numbers. So the parent function on a logarithm starts at 0 and then goes to the right, right? I have an asymptote there. You have to know the domain based on whether or not it's a rational function. If it's a rational function, I'm going to fall in a hole sometimes, right? Either that or fall off a cliff if it's asymptotic. You have to know, what are my domain values? I don't want to go sketching a curve that I don't have information on where it exists. Okay, so that's step one. Find the domain of the function. Then you're going to go from there to intercepts. It's really handy to find your y-intercepts. How do you find a y-intercept? No. Plug in 0. Plug in 0 for x, substitute 0 for x, and that places you automatically on the y-axis. If you want to find a y-intercept, you're going to put in 0 for x and go from there. If you want to find an x-intercept, a 0, what do? Set it equal to 0 and solve for x. So those are points, important points that show up on your function, and you want to know where those are. After that, you want to maybe consider symmetry. If it's an even function, it's symmetric on the y-axis, meaning that both sides look the same. That could really help you. If you're graphing a parabola and you find the points on the right side, you get automatic access to the points on the left side because it's even. That mirroring is important, right? Think of a trig function that is even.
Oh, the sine.
Not sine. Cosine. Cosine is mirrored on the y-axis. Cosine's an even function. Okay. Odd functions are reflections about the origin. So what I have up here on the right in quadrant 1 is going to be mirrored in quadrant 3. Does that make sense? Okay, so f of x equals negative f of x. No, that's even. F of x equals negative f of negative x. Go on the opposite direction. I have to think about that. Anyways, what's a trig function that's odd, that has the same thing up here that it does over here? Sine, tangent. Okay. Odd functions. Let's see if they wrote the rule right here. Yeah. F of negative x equals negative f of x. That's an odd. F of negative x equals negative f of x. For an even, f of negative x equals f of x. It's going to be the same on both sides. You would want to know like a periodic function. If they ask you to graph a trig function, you want to know, is it on 0 to 2 pi that it completes its whole period? Or is it on 0 to pi? What has a pi period? A period of only pi? Tangent and cotangent. Okay. After we find those things, the next things of importance are going to be your asymptotes. And I believe that I didn't get solid pictures of that. To locate horizontal asymptotes. How do we find horizontal asymptotes on a function? Say it louder. To find horizontal asymptotes, that means we're dealing with end behavior. Horizontal asymptotes are about end behavior. So how do I tell what's happening on the ends of my functions? If y'all were older, I would tell you to sing an Eagles song. You know the Eagles?
I do.
Anybody?
Yeah, tell me the song.
Take it to the limit. We're trying to find the horizontal asymptote. And so we look at limits at infinity. Limits as x goes to positive infinity, what does f of x do? If it hits like 3, then you know that this thing has a horizontal asymptote. As its tail goes to positive infinity, it's going to max out at 3. You had a problem like this on 4.3 homework. If you want to look at the opposite end, you take the limit to negative infinity. That's going to tell you what your tails are doing. Evaluate the limits at infinity to find your horizontal asymptotes. Okay. This information at the top up here is for vertical asymptotes. Why would a function have a vertical asymptote?
If you're evaluating
It's not defined.
Right, if it's not defined there. So it could be that it's a logarithm, and like we said earlier, I cannot log a negative number, so I've got a vertical asymptote at x equals 0 that keeps me from going anywhere beyond that. So how might I find the behavior of the function at that asymptote? Take the limit to the number. Take the limit to 0, and I know what the behavior of the function is, right? If it's a rational function, and I want to find vertical asymptotes, what am I going to do? Set the denominator at equal to 0. Then you're going to know whether you've got holes or asymptotes and where they're located, and then you evaluate the limits there. Yeah? Okay.
The holes in the asymptotes, how do you tell me?
Common factors. So if it's a hole, it's going to have a cancel buddy.
Okay.
If it doesn't have a hole, it's probably because he's an asymptote. He doesn't have a cancel buddy, right? Okay, slant asymptotes we don't do in this class. Slant asymptotes, those are oblique asymptotes. Those are pretty cool. We talked a lot about them in pre-cal, but they're not tested in calculus for us. Increasing or decreasing intervals. Now we get into the actual need for calculus, right? I want to know where my function's going up or down. So how do we do that? Right? So we run a first derivative test. Take the first derivative, set the derivative equal to 0 or
a positive number or a number above or a number below.
we say I'm looking for places where the derivative is 0 or where the derivative does not exist. Then we calculate all of our candidates. We put them all in a sign chart. And then we run the increasing, decreasing test. And we see, do we see changes in increasing, decreasing? If I'm going from increasing to decreasing, there is a maximum. And we go find that maximum value. If my function is going from decreasing back to increasing, what? Then we see a minimum value, okay? That brings us to F, finding local maximum and minimum values. You use your sign chart to do that. Letter G, we want to know about concavity and points of inflection. Which derivative are we interested in there? Second derivative tells us about concavity. If the second derivative is positive, the function is concave up. If the second derivative is, then the function is, and you can find those points of inflection by setting the second derivative equal to 0. Okay? And then you plug those numbers, those x values, back into what? Into the original equation to find the actual point of inflection. This changes at whatever. Yeah? Ready to try one? Okay, cool. Here comes example 1. We're going to do one example in this lesson. 1.
There's like a million here.
Uh-huh. So it says use the guidelines to sketch the graph. Doesn't that sound like clear and concise and straightforward? Use the guidelines to sketch the graph. Okay, so in parts, we're going to start off with the domain of this function. This is a what kind of function?
Rational.
This is a rational function. So its domain is going to exist only when the denominator does not equal 0. So in order to find that, we'll set the denominator equal to 0.
And choose every other number.
And then we'll use the quadratic formula to find the zeros here. Why would we do that? I saw that yesterday. Somebody did that. So x is plus or minus 1. X is all numbers such that x is not equal to positive or negative 1. This is our domain. X exists everywhere except right there at positive and negative 1. So when we get ready to graph it, we're going to draw what? Could be asymptotes, could be holes, we don't know. But we know that x can't be those numbers. Okay. Letter B. Find intercepts. So to find a y-intercept, what do? Yeah, we find f of 0. F of 0. So that's going to be 2 times 0 squared over 0 minus 1. 0 over negative 1 is 0. So what we know now is that we have a y-intercept located at where? 0, 0. 0, 0. On the origin, there's a y-intercept. Okay. We're also going to need to find x-intercepts. To find an x-intercept, what do? I set f of x equal to 0. It's a rational function. So I only have to set what? The top equal to 0. I could set the whole thing, but then my denominator is going to cancel off. So really, I'm interested in the top equal to 0. So x squared is 0. X must be 0. Looks like there's only one x-intercept here. It is also the y-intercept. So our x-intercept is the origin, and the y-intercept is the origin. Everybody okay with that? Okay. I'm going to hit that picture right here again because I want to keep looking at that graph. Okay, the next thing that we want to look at is we want to decide if this is an even or an odd function. That's going to help us with symmetry. So we're going to decide whether it's even or odd based on its symmetry. If the function is even, the rule is f of negative x equals f of x. That is even. Graphically, what that means is if I go way over here to negative x, I'm going to hit the same value that I do way over here on positive x. Even. Okay? If it's an odd function, f of negative x is going to equal negative f of x. This is odd. What that means is if I'm way over here at negative x, then way over here at positive x, it's going to match it, but it's going to be odd. Can y'all see that? So we're testing. We're testing here. Let's try f of x. Pick a number. What number you got? 1. I like it. Let's try f of 1. 2 by 1 squared over 1 minus 1. Not 1. 1 is terrible. We just said the domain can't be 1. Why'd I listen?
2 and negative 2.
I like 1. 1 sounds like a great option. Sorry, Brooks. We were both wrong. Pick 2. Pick 2. Try 2. If I plug in a 2, 2 by 2 squared, that's 4 by 2 is 8 on top. 4 minus 1, 8 over 3. Y'all agree? Okay. Now try negative 2. Drag it 8/3 again.
Yeah.
So what does that tell us?
It's even.
This is an even function, meaning what? Why is that helpful? It's got symmetry.
Couldn't we tell that by the degrees being?
Yes.
Yeah, that's what I thought.
It has symmetry on the y-axis. That's going to be important. Okay, symmetry on the y-axis. Okay?
Is it the highest degree of the square?
No, it's because everything got squared.
Is that
Everything's the same.
All right, letter D. Letter D wants us to find all of the asymptotes. If we're finding horizontal asymptotes, we're taking limits to infinity. I'm looking at the limit as x approaches infinity of f of x, which is going to be the limit as x approaches infinity of 2x squared over x squared minus 1. We could plug in. We're indeterminate, infinity over infinity, so then
Do something.
do something. You could do something algebraically, or you could L'Hopital.
L'Hopital is good.
L'Hopital is good.
Can't we only do that if we have to? Is that the thing, or we don't do that?
We could L'Hopital here. We could go forward and find this limit. What else could we do? Could we remember sitting in our Mentis class in Algebra 2, 1 or 2 years ago, where we look at the degree of the top and the bottom and they have the same degree, and so the 2, there's a horizontal asymptote at 2, at y equals 2. Because the limit, whatever, is 2. Okay, now let's take it to the left. Isn't that the exact same function?
Yeah.
So isn't it also 2? Okay, so what this tells me is there's going to be a lid. There's going to be a horizontal asymptote at y equals 2. Now, can the function cross the horizontal asymptote? Is that allowed?
Yes.
Yeah.
The middle area.
But in the middle, right? We're talking end behavior here. So as we approach positive and negative infinity, the ends will go to that asymptote. Okay, so that's not saying that it's a boundary it can't cross in the middle. Okay, now let's talk vertical and horizontal asymptotes. How do we find, vertical asymptotes? How do we find those?
Set the denominator equal to.
Yeah. To find a vertical asymptote, we're going to set this denominator, x squared minus 1, equal to 0. X squared equals 1. X is plus or minus 1. It's not enough to just know that there's an asymptote at 1. We knew that. We knew that when we did the domain. We knew that either it's a vertical asymptote or it's a hole, right? What we want to know is how the function behaves around it. So we're going to evaluate 4 different limits here. It's going to be fast. It's fine. We're going to evaluate the limit as x approaches 1. You're coming in from the right or the left first? From the left. The limit as x approaches 1 from the left of f of x. So of 2x squared over x squared minus 1. So plug your 1 in there. What did we get? 2 over 0. So the limit does not exist, but which way is it going? So we're coming in from the left. Let's let this be not 1. We know it's 2 on top, right? Let's let that be a number slightly less than 1, like 0.9. We're coming in from the left. 0.9 squared.
That'd be smaller,
That's the number.
It's going to get smaller, isn't it?
Yeah.
And then I'm subtracting 1.
0.18, right? Or no, 0.81. Because 99 and 81. So 0.81
So I'm subtracting 1.
minus 1.
So this is negative. This is negative small. Negative small, which tells me what? It's huge.
Divided by its one.
But it's negative.
So it's going to be
So it's going to negative infinity.
negative.
Okay.
Sense, I guess.
It depends on what direction we're approaching. Let's go to 1 from the right. Now we're going to be bigger than 1.
1.1.
barely bigger than 1. So when I square it, it's still going to be barely bigger than 1. I'm subtracting 1. It's going to be very, very small, but it's a positive small, which means this is going to go to positive infinity. Yeah?
Yep.
I've got good news for you. It's going to match on the other side. You know why?
Because it's even.
Because it's even. That's why we needed to know that. So the limit as I approach negative 1 from the left, limit as I approach negative 1 from the left, it's going to match, but it's going to be backwards because I'm approaching from the left. And so on the left, it should be positive. And on the right, it's going to be negative. You got to see it to see what I'm saying. On the left, at x equals 1, I'm just drawing a really, really quick sketch here. At x equals 1, from the left, it went to positive infinity. From the right, it negative infinity and then positive infinity. We need to see the same thing over here. Does that make sense?
Wouldn't it be?
Oh, it's going to be, yeah, I drew them backwards. It needs to go like this and like this so that it matches. So they match symmetrically, but they're backwards as far as the limits are concerned on the asymptote. In order to maintain that symmetry, you've got to flip the way that the limits read. Okay, I think that's good. I like. Okay, now we're to the calculus portion. So part E wants intervals of increasing and decreasing. Intervals of increasing and decreasing. So how do we find those? Take the derivative. That sounds fun, doesn't it?
Yeah.
So in order to take this derivative, it's a what? It's a quotient, and we're excited about that. So our derivative, f prime of x, is going to be low d high minus high d low, which is what? What's the derivative at the bottom? 2x. Square the bottom, and away we go. I think both of these are going to have a 4x in there. It's going to be x minus 1 times 4x minus 4x cubed. So what if we pull out a 4x in front? We have x squared minus 1 minus what's left. If we pull out 4x minus x squared, right? Isn't that all that's left? So I can cancel those x squareds. 4x times negative 1 leaves me negative 4x over x squared minus 1 squared. Okay. There's my derivative, f prime of x. That's the most simplified version. Now we want to do what? We want to find where f prime of x equals 0 and where f prime of x does not exist. So we set that derivative equal to 0, which means really I'm just setting the top number equal to 0. X equals 0, that's one of our candidates. Where does it not exist? where the denominator would be 0, right?
Yeah.
I got plus or minus 1 again. So we've got 3 numbers for our sign chart. 3 beautiful, beautiful numbers for our sign chart. What if I draw my sign chart down here? Is that going to be bothersome to y'all? No? -1, 0, 1. We are testing into f prime to see whether f prime is positive or negative, right? So pick a number less than -1. What are we going to get on top? A negative on top. What is always going to be on bottom? A positive. I think it's positive on top.
Yeah, it is.
Okay. So what does that tell me? If f prime is positive, what does that tell me about f? Increasing. Okay, pick a number between -1 and 0. Negative whatever, right? On top, it's going to come out positive. On bottom, it's going to always be positive. So positive over positive tells me f is still increasing. Pick a number between 0 and 1. Okay, on top, it's going to be negative. On bottom, it's going to be positive. So what's happening on f? Number greater than 0? I mean greater than 1?
Negative over positive.
We're doing all right here? Just wanted to note that this was a place where the function didn't exist. And this is a place where the function, or the derivative equals 0. Okay, so now we need to tell times when f is increasing and decreasing. For the purposes of time, I think we can summarize. Okay, so we know that the derivative is positive when?
Everywhere except like the real over here.
Okay, so because f prime of x is greater than 0, f is increasing on the interval what?
Negative infinity to 0.
Good. Negative infinity to 0. So because f prime of x is less than 0, f of x is decreasing on the 0 to infinity. Questions on that? Okay. So we found intervals of increasing, decreasing. Letter F wants to know, well, then what are your max and mins? How do we know?
Set the derivative.
We did. We just found it. F prime of x changes from what? From increasing to decreasing at where?
0.
At x equals 0. F prime changes from, F doesn't change from increasing to decreasing. I lied. F prime changes from positive to negative. Make sure you write that. F prime changes from positive to negative at x equals 0. Therefore, this little 3-dot triangle stands for therefore. I probably never use that. Therefore, f of x has a maximum value because it's going from positive back to negative, so up then down. Has a maximum at what?
At x equals 0.
At x equals 0, but what's the point?
Plug that in the original.
Plug it into the original equation. Our original equation is this guy right here.
Isn't that 0? It's the
So 0 on top, negative 1 on bottom. 0, comma 0. F of x has a maximum at 0, comma 0. Y'all still trucking?
Yeah.
We're nearly done. We're nearly done. The only thing left here is to figure out concavity, which is the second derivative. We've got about 10 minutes to whip that up. So, our first derivative, f prime of x, I think it's good to have that written at the top. F prime of x we found to be negative 4x over x squared minus 1. Okay, so we need to take the second derivative so that we can tell about the function's concavity. Also a quotient. Low d high minus high d low, a chain, 2 times x squared minus 1 to the first times 2x all over the bottom squared. I think both pieces have this x squared minus 1 business in there. I'm going to try to simplify before I pull it out. Okay, this is going to be plus because the negative times that negative makes a positive. 4 times 2 is 8 times 2 again. I've got 16x squared times x squared minus 1. Do y'all agree with that? So I'm going to pull that x squared minus 1 because I can see it here and here. Both terms have at least 1. So I'm pulling that to the very front. What that leaves me in my first term is that negative 4 plus 16x squared, period. I was only able to pull one of those from the first. That's going to leave negative 4 times one of them. Yeah. All over x squared minus 1 to the 4th. Why did I pull that? Because it can cancel. Cancel with one of those on the bottom. So now that'll be thirds cubed on the bottom. So on top, we're going to have negative 4. What if I push that negative 4 through right there? Negative 4x squared plus 4 plus 16x squared all over x squared minus 1 cubed. I got 12x squared on top plus 4 over x squared minus 1 cubed. I think that's my second derivative. And what are we going to do with that? Okay. So equal to 0, that's just the top equal to 0. I have x squared equal to negative 12 thirds, and I quit right there, or negative 1/3. That's a nope. It's imaginary. And then where does it not exist? That's going to be x squared minus 1 cubed equals 0. Cubed root it. X squared equals 1. X is plus or minus 1. So those are the numbers that I'm throwing in my sign chart. Yay! And we're testing increasing or decreasing. What if we finish right here tomorrow? Okay, I'm just gonna pause this though, and we'll try to just pick right back up here. Okay, we're just gonna try to finish this problem. We got 45 minutes into it, and then the bell about rang, and I just wanted you to have all of the information kind of in one place. The last place that I paused, we were looking at the second derivative test. We have found the second derivative to be 12x squared plus 4 over x squared minus 1 to the third power. We tested where does the derivative equal 0. We also set the derivative where it would not exist. That's this bit right here. So f prime of x does not exist. That's going to happen anytime this denominator zeroes out. When we did that, we found x equal to positive or negative 1. And those are numbers that we're ready to throw into our sign chart here. If we test a number less than negative 1, that's going to come out positive on the top and negative on the bottom. A number less than negative 1 is going to be squared minus 1 number less than negative 1. It's going to get squared, so it's going to be positive, and then it'll be minus 1. That'll be positive. So this is going to be f of x is concave up because f double prime is greater than 0. Next, I'm going to plug in 0. So if I try 0 into the top, I get a positive. If I try 0 in the bottom, I have a negative. So this is going to be concave down on the interval from negative 1 to 1. And then if I try a large number greater than 1, going to have the same kind of situation here if I plug in a large number greater than 1 as I did when I plugged in a number less than negative 1. So that's going to be a positive on top and a also positive on the bottom. So this is concave up on the interval from 1 to infinity. Okay, so we've got to do some justification here. We're trying to justify inflection points. And so there are no candidates for inflection points here because when we tried to set the second derivative equal to 0, we didn't get any. What we did get was 2 places where the second derivative does not exist. Those don't qualify as inflection points because they're actually asymptotes. So there are no inflection points. There are no inflection points on this function. Inflection points. Again, the reason for that is because over here, when I tried to set the derivative equal to 0, I wound up with some kind of imaginary situation, and that doesn't work. So the only candidates that we have here are not inflection points. They are places where that derivative did not exist. But we can still see that there's a change in concavity. And so if we're looking for intervals of concave up or down, we can say f of x is concave up on, let's see, negative infinity to negative 1 and 1 to infinity. And the reason for that is because our second derivative was positive. F of x is concave down on the interval between negative 1 and 1 because the second derivative in that case is negative. Okay? So now, if we put it all together, starting at the very, very beginning, and I'm going to get an actual grid here because why the heck not? Okay, so I'm going to kind of let my axis be located right here. And I'm going to do my my x-axis right here. Okay, so the first thing that we know is the function is asymptotic. the domain is at +1 and at -1. Okay, we knew that this function does not exist in those places. We also found that we have a y-intercept at the point 0, 0. Okay, we said that that's also an x-intercept at 0, 0. We know that the function is even, and so it's symmetric about the x-axis. We know that there is a horizontal asymptote, while we're in the nature of graphing asymptotes, at y = 2. We found that very early on. There's a horizontal asymptote at y = 2. We found that the asymptotes are at positive and -1. What else that we figured out is that the limit as x approaches +1 from the right, we found that limit to be infinity. So as we approach +1 from the right direction, we found that limit to be infinity. As we approached, so I'm just going to put this first part. We don't know enough to graph the next part. As we approached +1 from the left, we found that limit to be -infinity. So that feels like it goes down like this. As we approached -1 from the right, we also went to -infinity. And as we approached -1 from the left, that'd be up here, we went to positive infinity. So that was beautiful. Some more information that we found is that f is increasing on -infinity to -1. It's increasing. It's getting larger. So that feels like kind of what I've got going on right here. It's getting bigger. It is also increasing from -1 to 0. So in this area right here, we found that it would be increasing. It is decreasing on 0 to 1. So, looky there. It goes right down from 0 to 1. And then we found it was also decreasing from 1 to, as it went out to infinity, which is going to be here. Okay. F changes from positive to negative at x = 0. Therefore, f has a local maximum at 0. If you weren't sure about that, look right here. This is your local maximum, and it happens at 0, 0. That's cool. What else we noticed was the concavity changed directions. It was concave up on -infinity to 0, and that's this area right here, concave up. It was concave down on -1 to 1, so that's going to be this area right here. And then it was concave up again from 1 to positive infinity. Okay. So I think this is a really great showing of this picture. We've completely graphed it in its entirety. I can't think of anything else that we might be able to show besides just going in and plotting some points. But what I want you to really realize here is that we had the capability of graphing this entire function in all of its glory without ever picking up a calculator. And that is the benefit of knowing some calculus.